Thanks so much for this very kind introduction. It's my great pleasure to be back here in Uppsala to talk about a subject which is very favorite, very dear to my heart, especially these days. It's one of my favorite subjects. And that is the connection between string theory, which is what I've been working for many decades now, with the dark sector. So I would first try to give an introduction to what is the dark sector. I assume you do not know much about it, which may be the wrong assumption, but let me assume and start from scratch. In 1915, Einstein wrote his famous equation, which explained how matter curves space and time. In this description, he had the curvature of space-time on the left side of the equation, and the matter, energy, and momentum of the matter on the right side. So basically, this was the relation which explained how the matter, as represented on the right side, like objects, particles, and so on, affect the curvature of space-time. So this relation between what matter does to how the curved space-time was a geometric way that Einstein managed to describe gravity. So this was a way to describe how gravity works. It turns out his geometric formulation of gravity, it was one of the most beautiful, elegant connections between physics and geometry. He wrote this beautiful equation, but soon he discovered it doesn't work. Because he was not just interested in gravity, like just the planetary system and solar system or even galaxy, but he was more interested potentially in the whole universe as a laboratory for his equation. And so when he applied his equations to the whole universe, he noticed that this implies the universe would collapse. It's not stable. So he was disappointed because at the time, there was no evidence of any collapse. Stars were where they were. There was nothing amazing going on. They should have been stationary. It didn't look stationary. So he said, oops, I have to change my equation. It's not working. So he went back, what can I do? What can I do? And then he said, I can add one extra term to my equations. As scientists do, we have to fix the equations don't work. We just try and error. So in 1917, he put this term, what he called cosmological constant, a constant which fixed the problem for him. It's a number he put in there in this equation. And with suitable choice of that number, he managed to get a stationary solution corresponding to what could be our universe. Now, it turned out that that term was there to balance the curvature and the matter content together so that they don't move one way or the other. They're just kind of like stuck there. That was needed to fix the balance. In 1929, about a decade later, Edwin Hubble, the astronomer, discovered that the universe is actually expanding. It is not stationary. So Einstein suddenly found that it was not necessary to put lambda, the cosmological constant, in his equation. So because what Hubble discovered was that the farther away galaxies, the farther the galaxy is, so he looked at the distance of galaxies, and the farther the galaxy is, it looked more red to us. So it was shifted. The light that we got for it was more red. And when you come closer to us, it was more blue. So that suggested that the farther away galaxies are moving faster away from us because that would give the light coming towards us a red shift. And so from this, he found that actually the farther you are, the faster you're expanding away from us, suggesting that the whole universe is actually expanding, and the distance will be proportional to the speed of how fast they are moving away. So with that discovery of Hubble, Einstein went back in 1931, a couple of years after Hubble discovered it, and said, you know what, lambda is 0. I should have stuck to my first equation. And you take a flat universe and you let the universe expand, and no problem. It seems like it works very well. We don't need any extra term. And he called this biggest blunder of my scientific life. This was the beginning of the enigma of the cosmological constant, as we will see. So already went once up and down. from 0 to a positive value back to 0. At the same time, around the same time, quantum mechanics was coming to be discovered by physicists. And here you see Einstein and Bohr describing and discussing the puzzles of quantum mechanics. Einstein was not very happy with, even though he was one of the main contributors to the beginnings of quantum mechanics, he was kind of puzzled about how the quantum mechanics final formulation looked like. And in particular, the study of microscopic worlds seemed to be more geared towards the quantum mechanical description, where the particles, like electrons orbiting the nucleus of an atom, are best described by waves. And at the larger scale, Einstein's description was the relevant one, because at farthest distances, the main force of relevance was gravitational force. And these were successful, one for large distance and quantum mechanics at short distances, but they didn't seem to quite fit very well together. And in particular, in 1960s, a few decades later, Feynman attempted to combine this theory, which was so successful for the small world, the micro world, with Einstein's theory for this macro world, the same way he had managed to have good understanding of how quantum mechanics works for electrons and photons, quantum electrodynamics. It did not work. Feynman, as brilliant as he was, he had difficulty connecting the same methodology that was so successful for describing quantum aspects of electron interacting with photon as working for gravity. And in particular, when you try to describe the quantum aspects of gravity by particles, which would be the same way that he did it for electricity and magnetism, namely replacing that by photons, here replacing by gravitons, it led to inconsistencies that he did not know how to resolve. He gave up on that question. But about a decade later, gradually, by accident, a solution emerged. Physicists were trying to do something completely unrelated to gravity. They were trying to describe how the results of the accelerators, the scatterings that they were doing by taking particles at high energy and shooting at each other, and the things that came out, by trying to make sense out of it, they accidentally stumbled upon the following. They found that if you replace a point particle, or point particles in general, by loops of energy, which we can call strings, it turns out that you do get gravity in a quantum form as part of the excitations of the string, and the conflict between fundamental particles is represented by vibrating strings, the conflict between quantum theory and Einstein's theory gets resolved. So general theory of relativity that Einstein proposed magically got resolved in terms of its inconsistency with particles at short distances if you replace the particle itself with extended objects called strings. This started in late 60s, and by mid 70s, the basic ideas were in place. String theory leads to a potential unification of all particles represented by various excitations of string. It could be open strings, like intervals and with two boundary points, or like circles, which is vibrating in different vibrational modes. It turns out, depending on what kind of vibrational modes you have for the string, or what kind of geometry they are wrapping, and so forth, it could describe different particles, and it unifies all particles into one entity, which is quite remarkable. But it had some exotic feature. String theory did not seem to work in 3 spatial dimensions at one time. It needed more dimensions. So the way to resolve it was to assume these extra dimensions are so tiny that we don't see them in our experiments. In other words, the regular experiments we do are not sensitive enough to probe these tiny spaces. So therefore, one can think about these extra dimensions of strings as like tiny circles that are there everywhere in space, but they could vary even in size, but they're so tiny you cannot detect it. That was a resolution for these extra dimensions. Sounds fishy, doesn't it? Why does it sound fishy? Well, it sounds fishy because usually when you get a new principle, like extra dimensions, and they say, sorry, we don't see them, so push it somewhere else. I don't want to talk about it. It sounds embarrassing. That should not be the way. So in other words, the extra dimensions of string theory must be good for something. It's demanded by the theory that there are extra dimensions. Why aren't we seeing it? Let's see. Let's see, why don't we see it? We'll leave it as a puzzle for now. Now, quantum mechanics basically gives you a wavy nature to everything, including space and time itself. If you try to quantize Einstein's general relativity, since the general relativity deals with the curvature of space and time, quantum mechanics allows you to fluctuate the space and time, and it turns out that these fluctuations at the distance scales of about 10 to the minus 33 centimeters become so violent, the whole space and topology and all that stuff becomes completely ill-defined because it's so violent fluctuations happen at that scale. And at larger distances, this should give rise to a smooth-looking space and time, but not at shorter distances. So this will affect a lot of computations that one does. In particular, one of these, if you look at what are these consequences of these fluctuations, is that even if you set the cosmological constant to 0, as Einstein preferred at the end, quantum mechanical fluctuation bring it back to 1 in fundamental units of physics. So you cannot just say, I want it to be 0 and hope that's the case. The quantum fluctuations somehow bring it back. At least that's what it seems. But astronomers were computing, trying to see what would be the value of lambda in the equations, and the more and more they looked at it, they found that experimental values of lambda always comes back consistent with its being 0, namely much less than 1, and in fact even less than 10 to the minus 120. 10 to the minus 120 is ridiculously small, so here I just decided to write the zeros. So we knew lambda is less than that. Now, in fundamental units of physics, lambda is less than that. Naturally, this led physicists to believe that Einstein was right. Lambda is 0. We just have to figure out why the quantum fluctuations somehow go away and become exactly 0. Maybe there's a symmetry. Maybe there's some principle we are missing. In fact, we tried to show that 0 using string theory. We failed to show that lambda was 0. No matter what we did, if we assume the universe was similar to the kind of things we see in our universe without any particular extra symmetries like supersymmetry, it always gives lambda being non-zero. And so therefore, we couldn't understand why lambda was 0 in our universe. But of course, we were confronted with this experimental observation that lambda is so small, who would believe that it's not 0? Weinberg had a different view. In 1987, he said that there are many different, if there are many different solutions to the equations of a fundamental theory like string theory, there could be a natural selection process, that there could be different kinds of backgrounds which could lead to different values of lambda. And typically you might get lambda equals to 1, but there could be a huge number of other ones which give you tiny numbers. But you might say, why are we ending up with the one which is that tiny a number? And one way to explain it is that if you lived in a theory which has lambda was of order 1 or close to 1, you wouldn't exist. So what would that mean? If you were in a universe which has that lambda, you wouldn't exist means what? It means that if lambda was too big, the structures won't form. So the universe will be expanding so rapidly that you get no matter, no structure forming. No galaxies would form, nothing. Therefore, there will be no life. There will be no us to ask the question. This was called the anthropic principle. Anthropic principle means that you cannot say, if there are many universes, you can only ask questions that are natural only with a prior that you exist. So given the prior that you exist, you have to condition it on that. So if you say, for example, you're a living being, and you can say, what is the probability that you are connected to a ground somewhere? It's a very high probability, even though the chances that of choosing a planet in the empty space is very little, because you wouldn't exist in outer space. You will die immediately. So therefore, of course, you have to make it prior on your existence. And he was saying the same thing maybe is true about universes. If you have many universes, you have to expect our universe would choose this kind of a prior. And it turns out that the prior you need for galaxies to form and for potentially emergence of life is that lambda should be less than about 10 to the minus 120, consistent with observations, but not necessarily much smaller. So he said, oh, okay, so we are just at the border of the value which is natural for explaining why the structures form. Therefore, maybe the value of lambda is right around the corner around 10 to the minus 120. If that's the case, that will explain the smallness of it. And that he called the anthropic principle. So he proposed that it would be soon discovered. This was it could be soon discovered, and that would be a solution of why it's small. And about 11 years later, it was discovered by mapping the supernovae. Supernovae are these objects which you can try to use it as a kind of a distance ladder of finding where they are and how fast they are moving, and use that as a way to distinguish how quickly the universe is expanding. In recent times, they found, Perlmutter and Schmidt found that actually the expansion of the universe is going exponentially fast, and this exponential factor was proportional to the square root of this cosmological constant. And so this fact actually gave credence to the fact that lambda is not zero, and they measured it. And what they found was that it's about 10 to the minus 122, just around the corner from observations. That about the bound that Weinberg had predicted is exactly around the right value. So we had lambda was zero, lambda was not zero, lambda became zero, lambda became not quite zero, but close to zero, 10 to the minus 122. That was a big development. And ironically, Einstein's original model, his second equation, which added lambda back in, had a lambda which was about 10 to the minus 122. Ironically. So, of course, the universe that we are getting today is different from the one he was envisioning, because he was envisioning a universe which is curved like a three-dimensional sphere. But our universe is basically very much flat, so it's not quite the same universe, but accidentally, you get the same value of lambda. And the thing that causes expansion instead of Einstein's case, which was stationary, is that the universe is flat. The flatness means it's not balanced anymore, and it continues expanding. So that is the bizarre story so far for the dark, what is the cosmological constant, and what became known as the dark energy. Why is it called the dark energy? Because this value, the cosmological constant, even though it was put in by Einstein to solve a cosmological problem, it's actually physically an energy which fills the whole universe. It's like there's an energy in the entire universe. And you might say, what does it mean to have an energy in the entire universe? So you might be familiar with, perhaps, if you have seen potential energies or electric potentials. Usually we talk about the difference of potential energies to get the energy that we extract if we go from this height to the lower height. But the absolute value of energy makes no meaning. That's true without gravity. But with gravity, the absolute value, the actual value of energy makes sense. So there's a preferred zero, means unlike the usual thing that we're familiar with. And in this case, it turns out the absolute value of the energy determines how the universe expands, whether it's expanding fast, not expanding, and so forth. And it turns out that that is the physical meaning of lambda. So there is a tiny amount of energy per unit volume everywhere in the universe today. That is called the dark energy. Because why call it dark? Because we don't understand why there is such an energy. It's dark. That's half of the puzzle. The second half is the dark matter. So there are two parts to the dark sector of our universe. The first one was dark energy, which we just covered. The next part is dark matter. This started in 1930s by Zwicky and more quantitatively and more developed by the work of Rubin in 1970s. And the idea is very simple. If you have a matter, and if you have sun and if you have Earth here, you can find the speed in which the Earth goes around the sun, and the speed that the Earth goes around depends on the mass of the sun. Now, imagine many of these suns, these are the galaxies, are made of these suns, and these other suns are the other stars, which are these suns, various suns of each solar system of its own. These other stars are going around the center of the galaxy with some speed, which depends on how much mass is inside, which is related to how much visible star there is. So you can predict the speed that the stars take relative to the center of the galaxy just by simply counting and measuring the masses of the star inside. And you calculate this value, and you find that the calculated value is this red curve here as a function of distance to the center of the galaxy. But what you actually observe is not that red one, but actually the white curve. The white curve is the velocities that you measure as a function of the distance of these stars relative to the center of the galaxy, and it's bigger. Well, if it's bigger, that means there's more mass stuff inside than you predicted. Well, what it is, it cannot be a visible source because those you have included, so it should be a dark matter. You cannot see it. Now, you could say, well, maybe it's regular matter, you just don't see it, but it turns out that nothing seems to interact with these matter from various other experiments. We know that if it's there, it's going to be very, very different from our matter. So it's a different kind of matter, we know. And this is called the dark matter. In fact, there is more matter than just the visible one, which is the dark matter. And they have various properties. As I just mentioned, they interact very weakly, if at all, with non-visible matter and light. In fact, to date, we have found zero evidence for their interacting directly with regular matter or light. No direct detection of them. The only way we know is from gravitational impact. Namely, they interact with gravity. It is unknown, and it's different from our kind of matter, which is why we call it dark. It's unknown to us what it is. And another reason it's dark is that the photon and the actual light does not interact with it. It's more abundant than regular matter by a factor of about 5. 5 times more dark matter than regular matter. And it's cold. It's not going too quickly around. Like if it was going, let's say, 100 kilometers per second or something, then it will cause the galaxies not to form the way they do. So it turns out that their speed is not too high. So it's cold, and it's dark matter, and we don't know the exact origin of it. So if you look at the energy budget in the universe, about 70% of it is dark energy. About 26% or 27% of it is dark matter, and about 5%, a minuscule portion, is us. All the stars, everything you see is the 5% we're talking about. So 95% of the stuff is dark. So we are a very small minority. So essentially everything we know about our matter and so forth only applies to 5%. That's a humbling experience. I mean, after working so much on science, 95%, what is it? Now, this is the current picture of the cosmos, and we call it lambda CDM. Lambda stands for of course, the cosmological constant lambda, and CDM for cold dark matter. So this is the current model of cosmology, is having a dark energy lambda and the cold dark matter. So basically, the dark sector is what is the current understanding of cosmology. It is natural to ask if they are related. Could dark energy and dark matter be related? Well, they are both dark. At least there's a feature. We don't understand either one. Maybe they're both related to the same puzzle. That would be nice if they are related. Now I come to connecting these two, namely the dark sector, dark energy and dark matter, to string theory. Can string theory shed light on the dark sector? So the first question is, how does the dark energy get to be realized in string theory? String theory is a theory which does not have a free parameter. What does that mean? Well, if you measure, for example, the mass of the electron or the charge of the quarks or proton and so forth, you can use these measurements and put it in your theory by hand. However, in string theory, we are not at the liberty to put parameters in your theory. The string theory has no parameters. Instead, what it does have is choices of, for example, sizes of these extra dimensions or the shapes of this extra dimension that could be playing the role of parameters. So instead of saying, oh, I want the electron mass to be such and such, you say, oh, I want to have this shape for the extra dimension and this size for it and so forth. And by that choice, you're basically bringing in these information that you have. And of course, these values could potentially change depending on what shape and size you choose. So now, given that, it's natural to ask if extra dimensions of string theory can help resolve some of these puzzles of what they are. So one idea would be, suppose you have some of these extra dimensions. Think about it like a sphere or a circle or something. And suppose if you want to make the circle big, the energy goes up. If you want to make the circle small, the energy goes up. So there's just the right size for the circle for the energy to be minimum. Suppose that's the case. Then it might be looking like this picture here. Namely, you can think about this phi as the size of that circle, and this v as the energy of that. And you see that there is a minimum there, where the energy is minimum at some particular special tune value of this circle. If that's the case, then we would identify the value of this energy with the cosmological constant, and that would be a natural source for what we could call the dark energy. So somehow this would be preferred by this choice of trying to stabilize these extra dimensions for some particular value, and the energy that they get out is that lambda. That could be one picture. But in string theory, it turns out it's hard to do this, and maybe in fact impossible to construct such examples. We still do not have any reliable examples which behave like what I just told you. Two puzzles are there, both the value being so small and being a minimum surprisingly small is not easy to achieve. It's easy to draw a function with a minimum, just draw like this, but getting it in string theory turns out to be extremely difficult. Surprising. However, I will tell you one thing which is not difficult. Suppose instead lambda were negative. If lambda instead of positive was below the axis, was negative, then it'd be very easy to get a minimum. We have a huge number of examples in string theory where lambda is negative and everything looks beautiful. But for positive lambda, we have none that is trustable. Quite remarkable. Why is it difficult? Our universe is the one we want is positive, but that's the one which is not easy to get. The universe is playing hard to get. what we have instead, what we are sure about is the following. We don't know exactly what happens in these regions, whether there is anything like that or not. But what we do know happens is that if you take these sizes and make them extremely large, for example, typically what will happen is that the potential energy will go down to zero exponentially fast. This is typically the case regardless of whether you start with positive value of energy or negative value. Both of them seem to be going to zero. If there's a minimum with negative value, these are the spaces that we call anti-de Sitter space. That means we would live on a space called anti-de Sitter space if it were negative. If it was like a minimum like here, even though it's locally stable, locally metastable, it's globally unstable because it can decay because of the fact that the potential goes to zero at the end, this would have been called the de Sitter space. So what we are sure about is these regions is this way. And how do we know this? It turns out when sizes are big, string theory can do computations reliably. We can do computations in a reliable fashion because the strength of the couplings of string theory become weak, and therefore we can in principle compute these reliably, and we can be sure that it goes down to zero. And we have found that there are no solutions which are minimum very far away. So therefore, we are in this situation. So what do we do? These regions, faraway regions, are called the weak coupling regions because the coupling constant of string is small. You can actually do calculations. And we never get positive minimum there. And we cannot realize the cosmological constant in this way. So if you are in these faraway regions, the phi will start rolling. The phi, which means the size of the extra dimension, they start rolling, which means the extra dimensions either get bigger or smaller. They start rolling away. They wouldn't stay put. But experimental bounds show that this potential has a very tiny slope, less than 10 to the minus 122. Cosmology, if this extra parameters were there and they were rolling and the dark energy was changing or diminishing in time too fast, you would observe it. And we have enough observation to know it's not happening. At least the slope of the potential should be itself less than 10 to the minus 122. You remember when we talked about the V, or the cosmological constant, we said it should be less than 10 to the minus 120, and we said it's better be zero. And it wasn't zero. Here again, we have an experimental bound which is right on the borderline of dV d phi is 10 to the minus 122, and we don't have any reason why it's not zero, so it's natural to say it's zero. So therefore, you should look for a minimum or local minimum. That's why most physicists believe that the most natural solution will be to find the critical point, which is a minimum. Otherwise, how could it be so small without it being zero? However, it turns out that's not necessary. In 2018-19, together with some of my string theory colleagues, we studied more carefully and found that all reliable constructions of string theory, in the reliable regions at least, always satisfy a relation of the form that the gradient of the potential is itself proportional to the potential with a number of order 1 multiplying it. So if V is small, then we would naturally expect dV d phi to also be as small from string theory perspective. So saying that dV d phi is less than 10 to the minus 120 or 22 is natural from this perspective. So therefore, we said, oh, there is a priori no strong evidence that dV d phi is zero because it's natural to be of the same order of V, and that's about the bound like what we have now, just like the same kind of bound that Weinberg was getting. Here in this context, it's happening again to us, but now motivated by theoretical arguments of string theory, that's natural for the slope to be of this order. So we propose that maybe it always is the case that the slope is not zero ever, at least not a stable minimum should exist, and therefore maybe our universe is also rolling. Maybe the dark energy is not constant as we think. So we propose that dark energy may be depleting over time. We propose this despite the lack of experimental evidence for this at the time. In fact, I should say that we got some heat from my string theory colleagues because we were declaring that string theory does not accommodate observational physics, which says cosmological constant is a constant. We were saying we have difficulty with this, and we were kind of being honest. And they said, well, maybe you better not talk too much because you're saying that maybe string theory doesn't work. So nevertheless, we put out the paper, and no experimental evidence, and in fact, as I said, counter to the evidence, we proposed this. But let me continue. We also talked about what could be candidate for dark matter in string theory. Now, already back in 2006 and later in 2019 with a group of my colleagues, we had studied the following feature, that whenever you go to, in string theory, whenever you go to extreme regimes of parameter, like when you have extra dimensions becoming very, very big or even very, very small, what always happens is that you get always a tower of light particles. A tower, not just one particle, many of them, a tower of them, but very light. And the farther away you go in the parameter space, for example, the bigger you make these extra dimensional spaces, the lighter this tower becomes. The masses all go down. And they are weakly interacting with themselves and with other things. Their strength of interaction is very weak with everything, just like gravity. So this we had conjectured based on what is called the duality symmetries in string theory. So what does this mean is the following. When you go to these extreme limits, you find that your description of the physics breaks down and you have to have a different description. And the different description comes about by incorporating these other light modes that you get in these limits. For example, if you have one extra dimension getting bigger and bigger and bigger and bigger, at the end of it, the space is not three-dimensional anymore, it's four-dimensional. So you have four-dimensional space on one time instead of three on one. So the description of physics completely changes. So we say this is a dual description. This is the duality of string theory. And what are these tower of particles? Tower of particles are nothing but gravity waves in these extra dimensions. Standing waves of gravity, because this is like a compact little space. The gravity can go looping around it. And that state of the gravity is like as far as we can see, like a particle, like a standing wave inside these extra dimensions. So this is the picture I'm drawing here. So this is like the extra dimension, and the gravity is like a wave there. And the smaller the wavelength of this wave is, the more energetic it is. It's like a higher frequency. And if the extra dimension starts moving around, what's going to happen is that it stretches. These wavelengths will stretch, and their mass will go down. So you have a situation like this. You have a tower of light states, which as the size of these extra dimensions grow, they become light exponentially in the natural parameterization of this extra dimension with some exponent, and this exponent we can call C prime. Again, C prime is of order 1 number in fundamental units. Could these light towers be relevant for our universe? Could they be dark matter? Now, why are we raising this? You see, the cosmological constant is an extremely small number, 10 to the minus 122. I told you when you have extreme parameters in string theory, you're always near these large values of fields, because that's the only way you can get extreme values. And it turns out in that context, it implies naturally that you should expect, because the dark energy is small, because the cosmological constant is small, that there is a light tower. So we live in the situation with an extreme parameter. The cosmological constant is an extreme small parameter, Therefore, we must have a tower of light particles, which must be interacting weakly. What is this tower of light particles? We haven't seen them. Or have we? Could they be the dark matter? Could the tower of the light particles we're talking about, which is going to be hard to detect because they are gravitational interacting, they're weakly interacting, and that's always the case, as we know from string theory, could it be that's why we haven't been able to detect them? They are weakly interacting. So this will connect the smallness of the cosmological constant or dark energy with the existence of dark matter in the form of graviton or standing waves of gravity. Indeed, this has some nice feature. It unifies the dark sector, giving a connection between dark energy being small with the existence of this light tower, which could serve as the dark matter. And why it does not interact except gravitationally, and that's why we haven't directly detected them. So this would be an interesting potential way of thinking about it. And in fact, based on these ideas, with other colleagues, we found the only possibility is that one of the extra dimensions, out of these other extra dimensions that string theory have, one of them is bigger than the rest, and it's as big as a micron. Micron is 1,000th of a millimeter, or a micrometer, so basically. So this is a very, not super small, smaller than the size of a hair or something, but it is predicted to be the size of this extra dimension. How do we get it? It's related just to the scale of the dark energy. Namely, lambda has units of energy per unit volume, which can be converted to the energy to the fourth unit. And so if you take 1/4 power of it with a minus sign, you get a length unit, which ends up being around micron scale. So there's a natural length scale that gets connected with the extra dimension coming from dark energy itself. Moreover, the way to think about it is that we, the visible matter, we live on a slice of this extra dimension. So we live on a 3+1 dimensional slice, like a sandwich piece, inside one higher dimension. So the extra dimension is orthogonal to us. And we are like stuck on a plane, a 3+1 dimensional plane, if you can visualize, but I'm not able to draw the 3-dimensional space as a slice. So we'll think about it as if it's 2+1, sitting in one extra dimension, 3+1. That's the one I'm drawing here. But you can imagine that. So the galaxies and all that are stuck in the middle, like this shape I'm drawing here. So the visible matter is here. And this extra dimension, the dark dimension, is orthogonal to it. And the dark matter is the graviton that is living in this extra dimension. And how did it get created? Well, it gets created naturally because if at some point, if this is where the galaxies and us, we are formed, or we are there, if it's hot as it was in the early universe, it has energy, and energy couples to gravity, and gravity can produce a wave. So even though we cannot visit, we are forbidden to visit this extra dimension ourselves. So if you say, I want my spaceship to move into this micron scale dimension, sorry, nothing made of electrons and quarks and so on is allowed. It's forbidden. They're all stuck on this. And that's why, even though it's not that small, we cannot actually see that extra dimension. Only gravity can penetrate that extra dimension. But energy that is living on our universe couples to gravity, and therefore gravity that's created there can go anywhere, including the dark dimension. And we believe that what could have happened is that in the early universe, when the universe was much hotter, it created these waves of gravity going out, which when the universe cooled off, it didn't go away and became the dark matter that we see today. That's what the picture would be for how the dark matter works. And this was suggested in this collaboration with some other collaborators that I'm showing here. So in fact, this will be an interesting potential if it's true. It will be making a lot of other predictions as well. For example, it would suggest that the gravitational force should be stronger at shorter distances, because in 3 dimensions that we live, the spatial directions being 3, it turns out the gravitational force has an inverse square law. It goes like 1 over r squared. So if d is, d should be space-time dimension, I mean here. So if it's d is space-time dimension 4, you get an equation like 1 over r squared, which is the force that we have in our universe. But each time you increase the dimension by 1 unit, that power goes up by 1 unit. So if d becomes 5, 6, 7, etc., the power goes from 1 over r squared to 1 over I cubed. So therefore, it's natural to expect that we have a different force law, 1 over r squared becoming like 1 over r cubed, if your distances are small enough to be able to probe the extra dimension. In other words, when the distances are sufficiently small, locally the geometry as far as the gravity goes is symmetric between orthogonal and the direction that you're talking about, and you get a behavior which looks like 1 over r cubed. So that can be in principle checked. If you measure gravitational force at shorter distances, it should be stronger than Newton's prediction. Newton would have been wrong. So physicists have tried to check whether Newton is correct at short distances, and up to 30 microns is the world record. Newton is correct. So up to 30 micron, it's still 1 over r squared. And they are now pushing the limit down towards the 1 micron regime. Now, we do not know exactly what the value of this extra dimension is. 1 micron is a ballpark. It could be between, let's say, 0.1 to 10 micron if you want to give a kind of a ballpark estimate. So they're trying to reduce the distance scales to see if they can probe any stronger gravity force. And this would be presumably done within a few years. And the experiment kind of thing they are doing, this is a group in Vienna. They're doing this torsion pendulum. So they have a pendulum on one side, and they have a rotating disk on the other side with regions with higher and lower masses. And the pendulum on the other side also have regions of higher and lower masses. So when the higher mass regions are in front of each other, they attract one side, and when the other side goes, the other attracts, so the pendulum starts vibrating. So you rotate this disk in the natural frequency, resonance frequency of the pendulum, in such a way you start shaking the pendulum at a very specific frequency, and that's trying to detect it in that particular way. So you have an experiment like this, which is hopefully going to give some results for shorter distances. I think their current estimate is that they can get to 10 microns. Not necessarily to 1, but it's pushing the direction. And maybe if we are lucky, it's 10 microns. We cannot be sure what the exact length is. But anyhow, they are going in that direction. Within a few years, we might know what the answer is. But as I mentioned to you, we expect some of these parameters in the string theory are not fully stabilized, because we have had difficulty finding any situations where you have a totally stabilized potential. And therefore, it's natural to expect the extra dimension itself is not stable, and it's actually going to change size. So the 5th dimension could itself change size. And if it does, as I mentioned already, the dark matter itself will also become lighter. So we proposed in 2019 this model that maybe the potential itself is decaying with some extra dimension size, like e to the minus some constant times phi, and the mass, the dark matter mass, also is going decaying with respect to that extra size with some other parameters, c prime, where c and c prime are some order 1 numbers. And this, we call this the fading dark sector model. It fades because it wants to go down. The mass wants to go down, the v wants to go down. So these two constants, c and c prime, will determine the model. Well, we proposed this in 2019, and we also noticed from theoretical arguments that suggest the average value of c should be bigger than 0.82. So c was the exponent which was telling you how fast the potential is changing, the slope of the potential should be bigger than 0.82 on the average at least. And c prime the value of it should be order 1 up to a projection as a cosine theta, because it could be that the extra direction that you're moving is not exactly aligned in the fifth dimension. It could be some of the fifth dimension is changing and some other directions either are shrinking or growing, which are the smaller dimensions that you don't see. So they are not necessarily aligned. So this cosine theta is a misalignment between the direction of the dark energy and the fifth dimension, which we don't know anything about a priori. So C prime is like order 1 or smaller kind of value. We don't know exactly because of that cosine factor. But experimentally, we know that C prime cannot be too big. How do we know that? It turns out that this field phi, which is this extra size, is essentially like a massless field. Like itself is like kind of a photon, but in this case without spin. And it causes an attraction force like gravity between the dark matter, but not between the regular matter. So it's as if the dark matter has a stronger gravitational pull than it would have otherwise have. And the effect is increased by 2 times C prime squared for the gravity, for the fifth force, let's say, in the dark matter compared to its gravitational force. This fifth force, which is this new force acting on the dark matter, will be proportional to 2C prime squared. And experimental bounds from tidal forces on galaxies puts the bound that C prime is less than 0.2. So what are these tidal forces? So Milky Way is a galaxy, and then Sagittarius is this satellite galaxy, which is kind of came at some point close to our galaxy. And if it comes close to us, the dark matter, which is also part of our galaxy and part of the Sagittarius, will attract each other more than the regular matter. So there will be a disruption of the shape of the visible matter because they are displaced. The center of mass of them pull away. So it's a tidal force like the shape that we are familiar with, the tidal force on the Earth. That will happen to the galaxy. It will change the position of visible matter, and we would have some evidence. We have not found such an evidence. Puts an upper bound on how big this force could be, which is the bound I'm saying is C prime is less than 0.2. So these are the bounds we have. C should be of order 1 on the average bigger than 0.82, and C prime experimentally is less than 0.2. And so these are the data we have. And then we ask the question, is it true that our universe has C and C prime non-zero? Lambda CDM, this model of the cosmology we talked about, gives C and C prime order 0, should be 0. And it turns out when you do the calculation of cosmology with the cosmological model back in 2019, we found that our model was no better than the standard model of cosmology. So we were disappointed. We nevertheless published that paper because we found this theoretically very natural. But thankfully, the story began changing in 2024, 5 years after our paper. And this is thanks to 2 different groups in particular, the Dark Energy Survey, which is a survey of the sky in Chile, and another one, which is Dark Energy Spectroscopic Instrument, the DESI experiment in Arizona, doing experiments 2023, 2024, 2025. So a long history of these experiments, many years. And their data began coming out in the past couple of years. And we said, it's a good time to check our results. They found that the lambda CDM doesn't quite work anymore as good as it used to. So we said, let's check it, whether our results are working with this new model. And we checked it recently in the past summer. And we found that our model is actually better than lambda CDM by significant amount, the same amount for sigma that DESI team had found compared to lambda CDM. And we measured the value of C and C prime. We found C is -1, plus or minus 0.1, which is extremely nice because it's certainly order 1. It is bigger on the average than -0.82 that I was telling you about. And it's right on the ballpark. And C prime, I told you, it should be less than 0.2 by observational reasons. And it's indeed it's about 0.05. So the values are totally reasonable, as one would have expected. And so here, this red dot is where we land in terms of the C and the C prime. And these different colored contours correspond to how you combine the data that the DESI team had with the different supernovae data that people had collected in different experiments. And depending on which one you chose, you get different significances, but all of them, regardless of which color you choose, these contour plots, the light colors for each one of them is the 2 sigma significance being away, and lambda CDM, the standard model of cosmology, is C and C prime equals 0, which is down there, so it's really far away. And so this is where we are today. So it's this fading dark sector where the dark energy and dark matter are changing seems to be better than the model that people have for the standard model of cosmology, though the significance is still not enough to actually make us sure that's actually correct. In fact, since they originally put this data, the other teams, not the DESI team, have updated some of their measurements, and their significance went down from 4 to 3.2 sigma. So it's not like 5 sigma where we need to have our sureness that there's some discovery. So we are still not sure if this is the case. But look at the history, if this is correct, of the dark energy or cosmological constant for Einstein. 0 at the beginning, non-zero and positive next, and then 0, and then experimentally found to be non-zero and positive, and now it might be actually fading away. It's quite a history. So these values also imply that if you put them the value that agrees with the kind of things that I just told you about, C is of order 1 bigger than 0.82, and C prime is less than experimental bound of 0.2, gives you an attractive fifth force, which is 2C prime squared, acting only on the dark matter part, which is 0.5% as strong as gravity. So it's not as strong as gravity, but 0.5% of gravitational force. So these are all very exciting for string theory, and the cosmological analyses are still happening and continuing with the data. The whole data has not been analyzed yet. And the threshold of discovery is 5 sigma, which we are not there yet. And the Rubin Observatory, the new one, which has started last year in Chile, is now collecting data of supernova in a much more accurate way, a much more plentiful way. And within 10 years or less or so, we will know one way or the other. And it's natural to ask what kind of predictions we will make for our future of universe if this picture is correct. If you compute the order of events, if you continue with this kind of rate, you will get the idea that within 50 to 100 billion years, you go to the dual description of our universe, namely the universe that we live in. It's not going to be 4-dimensional, maybe it's 5-dimensional, and so forth. So we will find a new description of the universe. Of course, I don't think I'll be around to know exactly what happens then, but then it has to be a totally different universe. But that's the time scale, 50 to 100 billion. We're like 13 billion or 14 billion now. So we're like teenagers, and this is like, 50 to 100 billion. By the time you get old, you get a totally different universe. So let me conclude by saying that we have seen that ideas from string theory and quantum gravity lead to predictive unified model for dark energy and dark matter. The string-motivated model for dark dimension, this extra dimension, which we now call the dark dimension for obvious reasons, is currently one of the leading models fitting with cosmological models of the DES and DESI teams. And who knows, we may be at the cusp of a major discovery for fundamental physics. Perhaps this could be a first concrete evidence for string theory. It was a prediction. Thank you.
Thank you very much for the nice talk, and we will take a few questions. So, any questions?
Hi. So my question is more about let's say if you could explain more. So you said that there is a dimension, an extra dimension that we identified is about 1 micrometer, which is perpendicular to our 3D, right? And inside of it, what we understand to be dark matter is to be some kind of gravitons or gravitational waves that permeate this dimension, and this what we see as the dark matter. So what is the origin of these gravitational waves?
Yes, so I tried to explain with this slide, so let me go back to the slide, perhaps I went too fast. So here, so here I'm only drawing here the fifth dimension, the dark dimension. The other three dimensions I'm not drawing. So our universe will be this red dot here, which is actually that three-dimensional space, which I'm not drawing. Is that clear? Now, the temperature of the universe was hot at the early universe. Let's say it was, let's go back to the time where the universe was as hot as GeV. GeV is 10 to the 9 electron volts. So it's a huge, huge energy. At that time, since there is energy in our universe, and energy, remember the Einstein's equation, on the right-hand side was energy, and the left-hand side was curvature or gravity. So the energy that this universe has, namely we had at that temperature, creates gravity ripples, gravity waves. So that is the gravity wave is produced by the heat in our universe. It's like a piece of coal emanating radiation. That's roughly how you can think about it, which penetrates to the extra dimension. And this will be like a standing wave, if you want to think of it that way, which is this dark matter. Now, of course, it's just a tiny amount, because it's like if you have a coal which is hot, the glow that comes out of it is not as much as the energy of the coal, obviously. It's much less. And indeed, when it was created, it was a tiny amount of energy that leaked out. However, then our universe cooled off very fast because it was radiation energy, and the energy of radiation drops out very quickly to zero compared to matter. So the matter energy didn't drop down so fast. And therefore, after a while, the wave that it had created, that the after effect of that heat that it was, stayed around, and that became the dark matter. So the dark matter was created at the same time as the temperature was around GeV.
Okay, all right.
So, so when you mentioned the dark energy as having a natural zero, kind of, where is the dark energy located? Is it a form of like a kinetic energy or a potential energy?
It is the value of the energy. So you can think of it as a potential energy. Potential energy of something else. And something else could be the extra dimension, whose energy you're measuring as the dark energy. So the picture you can think about is that suppose the extra dimension has a given size, and if you try to stretch it, it causes energy. If you want to squeeze it, it causes energy. Then there's some value of it which you have to stock. But at that value, you can measure the energy that you had, because the absolute value of energy is measurable too. And that is the dark energy.
So I might not have understood everything correctly, but one of the last things you said with the universe potentially evolving into higher dimensions, does that mean that our current universe has already evolved from lower dimensions into this one?
Very good question. I wish I knew. But this means you're absolutely correct to ask this question. The early part of our universe should, in my view, also come from a dual description. It's very natural to expect that our universe was not forever three-dimensional. And whether the dual description is lower or higher or a totally different thing, I don't know. We don't have enough information. But I do believe it's much more natural to believe that it was a different universe. So our universe came and will go in that some period. And the beginning was, before it was something else, and later it will be something else. And we don't know if it becomes extra dimensional. In fact, it could also be that the extra dimension is shrinking, in which case you might think it becomes perfectly more and more three-dimensional, but sometimes it's not the case, that even if the extra dimensions shrink, there's some other description takes over which is very different. So we still do not know exactly where we are heading.
More questions over there. Yeah.
When checking for the fifth dimension, could we put a lot of energy into a micron to enhance the effect?
If we can put more energy to where?
put a lot of energy into a micron to.
Well, the only way we can put energy right now is using gravity. So, because as I said, you cannot take, for example, a beam of light laser and let me shine it that way, because light, photon, electron, etc., all are stuck on the three-dimensional one. So how can you make gravity? Well, if you make a huge, energy, like some blast of some huge gravitational wave produced, much, much more energetic than the one we are getting, for example, for gravity waves that we have. So, for example, we have measured the gravity waves. So that also creates some tiny wave in the extra dimension, but the energy is so small that's negligible. You need a factor of about 1 billion higher energy frequency to get to the region just to create the first few waves, ripples. So we are not there yet. So it's a huge thing. It cannot be done so easily.
I wonder, why is it specifically 1 micron? Is it some kind of information bottleneck, or?
So actually, it's related to the value of the dark energy. You see, let me give you an explanation here, which is, let's see, where did it go? Oh, here. So, let me explain a little bit about the dimensional analysis in physics. So, length scale, like wavelength, is inversely related to frequency. For example, when you have a light wave, when you have a longer wavelength, you have a shorter frequency, and if you have a shorter wavelength, you have a longer frequency. So the frequency goes inverse to the length. Frequencies also can be viewed as related to the energy. So the higher frequency waves, for example, have higher energy. So the energy and length go inverse to each other. Cosmological constant is energy per unit volume. So it's energy divided by length cubed. But length has unit of inverse energy, so it becomes energy to the fourth. So if you take the fourth root of energy, you should get a unit of energy. So you take lambda and raise it to the 1/4 power, that's energy. But as I said, energy is like an inverse of length scale. So you invert the scale, so you get lambda to the -1/4. So that's a natural unit that you get from the dark energy, and that becomes around the micron. So the size of this extra dimension will be related itself to the dark energy. That's why it's micron. Now, you might ask why the dark energy is whatever value it has, 10 to the -122. And that's one I don't have a good answer other than anthropic principle. That is, if it weren't, we wouldn't be asking the question. So it ended up being small. Given that it's small, then it makes these predictions.
I can as well ask a question. I find it fascinating that you can test the fifth dimension with a simple pendulum. It feels much cheaper than look at the supernova. So my first question is, how much will it constrain? Like, how well would you go to, let's say, 0.1?
Not easy. Right now, there are no methods known to go beyond 10 micron. The problem is that, gravity is so weak and things can interfere. For example, if you take two objects near each other, if you have some stray electrons moving on that surface, since electric force is humongous compared to gravitational force, it messes up the whole thing. So you have to get rid of individual electrons. How do you do it? Well, you try to put a shield which kind of blocks the electric field coming, what we call the Faraday shield. But that's going to be a big object, and it kind of, if you want to be a thin, big object, smaller than a micron, it will kind of bend and tilt. You have to make sure it doesn't bend, otherwise it will hit the pendulum and so on. So it's a big, difficult challenge to do. Now, I'm not saying it's insurmountable. For sure, I think people could have ideas to improve the technology, and we are going gradually down. So back, 30 years ago, it was the state of the art was only a millimeter or so. We only knew that Newton's law was worked up to a millimeter, but not less. Now it's been pushed down to 30 microns. Now maybe it's pushed down to 10 and 1 micron in the next decade or two. We will find out.
Yes, I don't think I quite understood why is it that the like quote unquote ordinary matter is like trapped in the three spatial dimension? Why can the normal matter not penetrate into the extra dimensions?
Good question. So we have discovered that there are these kind of objects in string theory where things are stuck on it. Like, so I told you that there are two kinds of strings: the strings which are closed and there which are open. It turns out there are what we call defects or D-branes, for which these strings, when they're closed loose, and when they come to it, they kind of open up. The boundary is stuck on it. So the ends of the string are stuck on it, and these become things like electrons and quarks and so forth. Now, so this can happen. Now the question is, why am I saying it should happen this way? Is that if indeed we lived, if the electrons and photons and everything lived in this extra dimension, then you can ask, what is their wave profile in this fifth dimension? Well, the lightest profile would be constant profile. So the lightest electron will be the no profile. But then there will be a version of the electron which has one harmonic, and then two harmonic. And then what you'll get will be a tower of electrons whose mass differ by electron volt. That's not true. Our universe, we know that there is no tower of electrons. We just have one electron. They are not separated by these tiny electron volts. So it better be that we are stuck.
Okay, I think on this positive note and on the prediction that in 100 billion years we will become 5-dimensional, let's thank Cumrun again for very nice talk.
Thank you. Thank you.